Okay, so thermodynamics. This unit is actually two half units combined. Thermodynamics has to do with energy, and the other half unit is electrochemistry. Electrochemistry, in and of itself, here is not a full unit's worth, but they work nicely together because they are so interrelated. So, for thermodynamics, we actually started studying thermodynamics a little bit when we studied thermochemistry. Remember when we used the heat equation, Q equals mc delta T, and delta H, right, enthalpy? So that's actually a big part of thermodynamics. So you already have your feet wet in terms of what enthalpy is. We're just going to teach you a couple new terms and then tie it all together. Because once you understand thermodynamics, you will now have a greater understanding of why all of the reactions that we have carried out throughout this entire course have happened. You'll be able to discern which ones will, which ones won't happen, and what the reason is. Right? Whereas so far, you probably were just guessing as to why some reactions do happen and some don't. Okay? So, first, definition: thermodynamics, the study of energy changes in chemical reactions, the effect of temperature on those changes. We've mentioned laws of thermodynamics before, right? So the first one, you know this, it's the energy of the universe is constant, right? So the interpretation we've been using here is on a microscale, meaning that energy can be neither created nor destroyed, right? So we've mentioned this before, and this is something you learn in physics as well, right? If there's a ball sitting at the top of a hill, it has X amount of potential energy, and then if it rolls, that potential energy turns into kinetic energy, right? And you can calculate that. There's no energy lost, it's just converted. So that's essentially what that is saying. So, new term, important term. Reactions that proceed of their own accord are termed spontaneous. And when we say proceed on their own, it means it doesn't need any extra help. It doesn't need any extra energy, doesn't need a nudge to happen. Any reaction that will happen on its own is a spontaneous reaction. Okay, that's simply put. So, things that will happen on their own. Rusting, right? So, if you have a piece of metal, scrap metal, sitting outside and it's exposed to water and oxygen, it's going to rust. There's absolutely nothing that's going to stop it. Will it rust instantly? No, but it will rust. Okay. An egg falling and breaking. If an egg falls off this lab bench, it's going to break. I don't think I've ever seen an eggshell so strong that it would withstand breaking after dropping 4 feet. Right? That's a spontaneous thing that's going to happen. Gases mixing if containers are opened. Right? So if you have 2 containers and you just kind of open the valve, they are going to mix, and if you do nothing, they will mix. That is a spontaneous thing that's going to happen. Water freezing if below 0 degrees Celsius. Well, water freezes at 0 degrees Celsius. It also melts, or ice melts at 0 degrees Celsius. So if the temperature is below the threshold, if it's below the freezing point, it's going to freeze. Right? That is well established. Okay, so all of these things will happen. They don't need any additional help happening. Now, even though a reaction may be spontaneous, it does not mean that the reaction is fast. The reaction could be fast, but it could be slow. The speed of a reaction has nothing to do with thermodynamics. We actually had a unit on speeds of reactions. We called it kinetics. Okay, so that's a big thing that you kind of got to wrap your head around. Just because a reaction is spontaneous does not mean it's fast. Okay, some are, some aren't. Now, we studied equilibrium, and we know that reactions are reversible. They can be reversible, some of them. So reactants that are spontaneous in one direction are not necessarily spontaneous in the reverse reaction. Think of like a one-way reaction, right? It happens in one direction, but doesn't happen in the other direction. That's what we're talking about. Reactions that can be spontaneous in both reactions are capable of equilibrium. And then you show 2 arrows. All right. So, processes that are spontaneous at one temperature may be spontaneous at other temperatures. I'm sorry, maybe non-spontaneous. So again, the melting of ice, right? If you're above 0 degrees, it makes sense that the ice is going to melt. But if you're below 0 degrees, it's the reverse process that's going to happen, right? So ice cube, puddle. So this process is endothermic, right? If you add more heat, the forward reaction is spontaneous. If you remove heat, the reverse reaction is spontaneous. Okay. So is that making sense, the term spontaneous? Reactions that will happen. Okay? All right. So there are two main factors when determining whether a reaction is spontaneous or not: enthalpy and a new one called entropy. Let's review enthalpy real quick. So enthalpy is the heat content of a substance or system. It cannot be measured directly, but its changes can, which is why we've pretty much always used delta H. And the typical units are kilojoules per mole. Now, let's review a second here. At constant pressure, we equated H to Q, right? The change in H to Q, remember that? So all of the reactions we were carrying out in calorimeters in the lab, because the pressure was not changing, that is how we were able to solve for a delta H value using water in a calorimeter. Okay, but that again, that's only with the specific caveat, constant pressure. Standard enthalpy of formation, the heat of formation of 1 mole of substance from its elements under standard conditions. The standard conditions, of course, being 1 atmosphere and 25 degrees. And remember, we spent a fair amount of time talking about what is a standard heat of formation reaction, what is not, right? So, for example, Ag, its standard state is solid. Chlorine is a gas and it's diatomic. So this would be an example of a standard heat of formation reaction. The delta H for this would be delta H F and have a degree sign. Degree sign indicates standard conditions. Now, if you were to see other examples of this, the main thing is understanding what is in its standard states and what is not, right? So if I gave you Ag liquid, for example, plus chlorine, that would not be a heat of formation because liquid is not silver's standard state. And these are the values that are on your thermodynamic data sheet, the delta H values. They're all delta HFs. We can use these heats of formation, these enthalpies of formations, to find the delta H of the reaction. Products, the sum of the products, and multiply by coefficients if there are any, minus the sum of the reactants, delta HFs, right? We've used this several times. This is how we get our theoretical value, right? And this is, again, if you're using chart data. If the value is negative, then you know it's exothermic, and it should be denoted by a negative sign. Negative. If the sign is positive, it's endothermic, right? Meaning the reaction absorbs energy from its surroundings. This was often a confusing point during lab, because sometimes we would carry out a reaction and the contents, the solution, would appear to get cold. The reason why the solution gets cold is because it's the water that's getting cold, but the reaction is gaining the energy from the water. So from the system's perspective, it's positive, right? If the water gets hot, that's because the reactants are giving off their heat to the water, meaning the reactants are losing energy, and that's why it feels warm. So these require a little bit of thought, experimentally. Okay, we good on enthalpy. You guys remember most of this, hopefully? Okay. Okay, so new term then. Let's talk about entropy. Entropy is a measure of the tendency for energy to spread out or disperse. Energy that spreads out or disperses. If your energy is dispersed, your ability to do work is lessened. Right? You have less ability to do work if the energy is now kind of just diffused. So, in other terms, it's what's considered a measure of disorder or randomness. Now, entropy, just like total energy and enthalpy, is a state function. Recall we mentioned state functions briefly back in our thermochem unit. So state function, this is a function that's independent of pathway. It doesn't matter how I earned $20, right? Some people earn $20 easily. Some people do it very laboriously. The end result is two people have earned $20. They did it different ways. A company can earn profits one way or another way, right? So at the end of the day, it's just what is it? What is the value? That is what we mean by state function. We can calculate the change in entropy, the final entropy minus the initial entropy, right, for any individual system. Okay, a little useful tidbit here is that if you're having a reaction taking place at constant temperature, a scientific word for constant temperature is what we call isothermal. Right? Iso means constant, essentially, thermal, so the same temperature, same amount of energy. The change in entropy is equal to the heat that would be dispersed divided by that temperature. So, in other words, delta S for the surroundings, sorry, it's too small. Is the Q of the reversible reaction divided by the temperature, whatever the temperature is. All right, this is a minor point. I threw this equation in here. I wasn't quite sure how much you would actually need it, but I just put it in here. And the reason why I put it in there is to make you aware of the delta S. There's two delta S conditions. There's delta S of the surroundings, and there's delta S of the system. The system, again, of course, is your literal reactants and products, right? Meaning here, like this one right here. When we take delta S is equal to the S final minus S initial, that's when we're talking about the system. You can use entropy values here from your thermodynamic data sheet. There was a column of data that we have not used up until now, and that was absolute entropy values for each of the compounds. So if I gave you a reaction and said, find the change in entropy for this reaction, you would use those values, products minus reactants. Okay, and that's how you would find the system entropy, change in entropy. Now, the second law of thermodynamics says that the entropy of the universe increases for spontaneous processes. So there's a simple equation. It says that the change in entropy for the universe is equal to the change in entropy for the system plus the change in entropy for the surroundings. And if these two are for spontaneous reaction, then that value will be greater than 0. Right? But if it's for a reversible process, then it's just set equal to 0. And frankly, we're not going to worry too much more so about that one. We're more so worried about this reaction. Actually, the most important reaction that you're going to be concerned with is here, this one. That's actually the only one you really be calculating. You might calculate this later, but those two. But the point of giving you these equations down here is to highlight simply the second law right here. For a spontaneous reaction, the total entropy increases. The total universe entropy increases, okay? The textbook will re-explain all of this, but sometimes the textbook gets a little too heady and you kind of get lost in the weeds, right? So this is a good one to rewatch videos like on YouTube about, okay, to get a better understanding of it, of entropy. All right, so as a result of all spontaneous processes, the entropy of the universe increases. That's what I highlighted, okay. Now, let's talk specifically. Entropy is related to 3 types of motion in molecules. The first type of motion is called translational motion, right? Translational motion, this is what we're literally when a molecule moves from one place to another. Can the molecule move? Does it move from point A to point B? That's called translation. Okay. The second type, vibrational motion. Do the atoms in a molecule move? Remember we talked about a bond, any kind of molecule, right? If there's a bond, that bond right here, what is this really? The bond is really a sharing of electrons, right? If this is a covalent bond. And if it's a sharing of electrons, that is predicated on the attraction of electrons towards both nuclei. The reality is this bond length, it's not like it's a stick. It's not an absolute length. These atoms vibrate and they oscillate. At 1 second, they can be closer, and then they could be extended, right? They could be farther. They're constantly, think of just a spring, in, out, in, out, in, out, in, out. The average distance between them is the minimum energy, and that's the compromise between attractions and repulsions. So back in bonding, I showed you a graph like this. Energy versus distance. And we saw a picture that looked like this. Remember the minimum point here, the minimum energy is the most stable position, the most stable distance between the 2 nuclei. We called that distance the bond length, but just understand that the atoms do bounce from each other, they vibrate, okay? So that's what we're talking about when we say vibrational motion. Okay, the third type of motion in a molecule is rotational, right? Molecules rotate. The same molecule just rotates around and around and around and around. The more rotates, then the more entropy it will have. So Boltzmann, who studied a lot about particulate energies, positions, and entropy, said that molecules of a sample, if you were to take a snapshot of them, that would be like taking a sample of their disorder at any moment in time. He called that a microstate. And so in thermodynamics, each state has a specific number of microstates. So let's examine the 3 states of matter. All right, on the far left, we have solid. In a solid, we have a rigid crystalline structure. The motion in a solid is restricted to vibration only. Okay, so these molecules, they can kind of, fudge in and out a little bit, wiggle in and out a little bit, but they cannot leave their position. There is no translational movement. You guys understand that? They can't get up and leave. So there's no translation. There is no rotation. They cannot rotate because the specific bond angles that exist are predicated upon the attraction between positive and negative dipoles of those molecules. Right? If I were to zoom in closer, This is delta positive. This is delta negative. There's a reason why these molecules are oriented this way, because that is how the attraction happens. And they have to stay that way, hence no rotation. So the only type of microstate available to a solid is vibration. Let's look at water. So in water, there's increased freedom with respect to translation, meaning molecules can move. Granted, how far are they moving? This molecule right here, this guy right here, how far is he going to move? He can move here eventually. He can move here and here, but it's like steps. It's not a gas where it can shoot straight across the medium, right? It's got to wiggle its way through. It's just like if you were at a concert and you were at the very, very, very front, right in front of the stage, but you had to leave. How fast are you leaving that concert? It's going to take you like half an hour to get to be able to leave, the grass, the field, right? Okay. They are free to vibrate, of course. Everything's free to vibrate. And then they are free to rotate. So in a liquid, there's a far greater amount of microstates, right? You have all three, actually. And then in gas form, you've got complete freedom for translation, vibration, rotation. If this molecule wants to go straight across here, it's very, very unlikely it's going to hit another molecule, right? Because there's so much space in between molecules. So the translation microstate is complete. All right. So freedom of movement. Which has the greatest freedom of movement? Gases. Why? Because they have high degrees of vibration, translation, and rotation. Which is the most restricted movement? It's the solids. Why? The only type of microstate that they have is vibration, and liquid is in between. Okay. So the entropy increases with the number of microstates within the system. So the number of microstates, therefore entropy, tends to increase if the temperature increases. Think about this. If the temperature increases, what is happening? Your molecules are wiggling more. If they are able to move, they're moving faster, and they're able to rotate faster. Okay? If the volume increases, how does that affect the microstates? If the volume increases, it doesn't change the vibration so much, it doesn't change the rotation so much, but it does change the translation, right? You're increasing translation to a large degree because there's simply more space to move to. And the number, if the number of molecules increases, the total amount of movement increases. And that is an increase in entropy. All right. So, you got this weird concept of microstates, of molecules wiggling and moving. So, in general, if we could generalize, what would we say? Entropy increases when gases are formed from liquids and solids. Okay, so if there's a reaction like either sublimation or vaporization, right? So solid becomes a liquid, right, which is melting, of course. Or solid becomes a gas, right? So that's sublimation. Both of these have positive delta H. Oh, of course, liquid to gas. Those are all examples of, I'm sorry, I wrote the wrong symbol. Not delta H, S. We're talking about entropy, delta S. Positive delta S, positive delta S. If there's more movement, entropy increases. Liquids or solutions are formed from solids. Okay, so we already addressed the liquids forming, but what about solutions? If a solution forms, entropy increases. Okay, so for example, NaCl in solid form, dissolving to become NaCl aqueous. Well, what does that mean, aqueous? Aqueous means it has been dissolved. It means the ions are now separated from one another and moving independently of another throughout the entire solvent. Right? A picture. Here's a chunk of salt. Here's a solution. They're all moving in a solution. Your entropy is much, much higher. Okay. Number of gas molecules increases. How could the number of gas molecules increase? Well, maybe something like this. If we have a decomposition of a gas, so N2O, decomposing, and we get O2 and N2. So even though everything here is a gas, right, so we already have a higher state of entropy, we have more moles of gas product than we do reactant product. 3 moles product gas versus 2 moles a reactant gas. This is an increase in entropy because there's more possible arrangements for particles to be if there's more particles that are independent. Okay, and then if the number of moles increases, right? So decomposition, basically. Yeah.
So, okay, I guess this doesn't apply to the N2O reaction, but suppose there's a reaction that increased the moles, the products were increased, but it started with like gases and then one of them went to liquids. Would the entropy still be negative?
So no. If you end up forming, if one of your products becomes a condensed state, that's actually negative entropy.
Right, I think that's what it is.
Yes.
Oh, okay.
So no. So it would not. So what you have to do is you have to look at the gases and solids effectively have similar entropies, right? So you want to look at what the change in the gas moles are. Did you end up with more moles of gas as a product, or did you have more moles of gas as a reactant? That's what ultimately, that's the biggest determiner of what the entropy change is going to be. Yeah. Okay. So, remember this term? Absolute zero. Absolute zero is defined as the lack of all atomic motion. Right? The temperature when all atomic motion stops. If all atomic motion stops, that includes vibration. That means nothing is vibrating, right? Literally still. So the entropy of a pure solid at this temperature is 0, which makes sense because nothing is moving. There are no microstates in action. Okay? So on your thermodynamic data sheet, you have a list of entropy values, and here's an example, a shorter one, right, of some values here. Notice that your entropy, right, so this is taking standard state, so this is referring to one atmosphere pressure and 290 or 25 degrees Celsius. 25 degrees Celsius. And this is a good time to review standard conditions. Standard conditions thermodynamically, 25 degrees Celsius, 1 atmosphere. Standard conditions for thermodynamics is not STP for gases. Anybody remember what the standard temperature for gases is?
Just
0, right. So be careful, okay? If ever in doubt, guys, just look at the top of the table you're using. It'll say 298 Kelvin, right? It doesn't say 273, okay? So anyways, These are just the samples, and notice how the units are different. They're not kilojoules per mole, they are joules per mole Kelvin. They can be written as kilojoules per mole Kelvin, but you would just have to convert. My point is, though, there is a Kelvin component to entropy, whereas there is not for enthalpy. The enthalpy unit is just kilojoules per mole. Okay? Again, and the units will always be listed on any table that you're looking at, so pay attention to it. Okay? All right, so these are the molar entropies for these substances in their standard states. And when I say molar, when we say molar, we mean per mole, like per 1 mole. Okay, so the absolute entropy for hydrogen, for 1 mole of hydrogen, is this, 130.6 joules per mole Kelvin. Obviously, because it's per mole, then we can apply stoichiometric ratios to this as we need to. Now, standard entropys increase with increasing molar mass, complexity, size. So what we mean is this. Here's methane. Methane's standard entropy is 186.3 joules per mole Kelvin. This is ethane. The reason why it has a greater molar entropy per mole is because the more bonds that are present, the more oscillations that can take place. Right? So you go from one molecule. Imagine if you made this with springs, right? And how jiggly it would be. You know, and you make it, you add more atoms, how much more jiggly it would be. And this guy over here would just be crazy. Right? It'd be wobbly, jiggly all over the place. So you increase the number of bonded atoms, you're increasing the number of oscillations. So that microstate is increased a lot. So hence more greater entropy, okay, per mole. All right, so getting down to the nitty gritty. In nature, there's greater chance of disorder than order. Okay, so when we say that, it's easier for things to be dispersed and spread apart than they are to be organized. Right? A prime example of this is, have you ever played 52 pickup? You guys know what that is? Oh, we should play. You guys don't know what it is. So you take a deck, say to your friend, let's play 52 pickup, and you just toss the cards at them, and now there's 52 cards all over they have to pick up. Right? What is the ordered state? What is the disordered state? There's really only one way for those cards to be ordered, but there's infinite ways for those cards to be disordered. Like the literal place where those cards fell, they could be rearranged in infinite number of ways. But to have them in order, like, you know, ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, you know, and so on. So it's easier for things to be disordered. It's just more likely. The tendency is, you know, if a volcano erupts and shoots out smoke and rocks, right, and those rocks land randomly around the landscape, do those rocks that come from a volcano explode and then land in brick-like fashion to make a castle? That'd be pretty cool. But that doesn't happen, right? That's too much order, and the tendency is for disorder. Okay, nature tends to be disordered. All right, so associating signs. Get used to seeing that if it ends up in a more disordered state, then it's positive change in entropy, because entropy means disorder. So there's been more disorder. Any reaction that results in more ordered is negative delta S. If you make something more orderly, you have reduced the disorder. Okay? And we talked about this before, how you can calculate products minus reactants, okay, using standard molar entropies from your table. So, having said all of that, take a second and make predictions about these 5 scenarios. Just put a positive or a negative next to them if you think there's positive delta S or negative delta S taking place. All right, so if I were to dissolve salt in water, would that be positive change in entropy or negative? Yeah, so ask yourself, are things becoming more disordered or less disordered? It's becoming more, right? Because your ions are now spreading out randomly throughout this entire beaker of water. That is a positive delta S. Taking dry ice from a freezer, now remember dry ice is CO2, solid form, and just setting it on your counter. What's going to happen if dry ice is just sitting on your kitchen counter? It's going to turn to a gas. So is that positive delta S or negative delta S? Positive, yes, positive. The gas form is more disordered than the solid form. Condensing water vapor to liquid water. Positive or negative delta S? It's more ordered as water. So your disorder is lessening. So negative delta S. Calcium carbonate decomposes. So CaCO3, solid, decomposes to calcium oxide, which is a solid, and carbon dioxide gas. Positive or negative delta S? It is positive. And then combining hydrogen, which is a gas, plus oxygen, which is a gas, to form water vapor, so still gas. But what is happening? Everything's a gas, so there's no obvious change here. But what is happening numerically? Yeah, you're going from 3 moles of gas to 2 moles of gas, so in effect, you're becoming more ordered, right? So more ordered is negative delta S. Okay, so at the beginning of this lesson, we talked about how entropy and enthalpy both dictate whether a reaction is going to be spontaneous or not. What we have to do for every reaction, we have to gauge both of those to make a decision. So let's take these one at a time. Actually, before I take these one at a time, let's take one step back and reevaluate coordinate diagrams for enthalpy. What's the delta H value for this graph? Don't give me a number, just give me a sign. We have a loss, right? Okay. Okay. So, nature has a tendency to reduce its energy state. You remember me saying this? This is kind of like a theme. It's always in the background of everything that's happening. So, between an endothermic reaction and an exothermic reaction, exothermic reactions are generally favored because we are lowering the energy state. Okay, so that means negative enthalpy changes. So when we consider a reaction and we determine what the signs are for both enthalpy and entropy changes. Okay, so scenario 1. If your enthalpy is negative, that is favored. If your entropy is positive, that is favored. Both factors will favor the reaction, so that reaction will definitely occur. Okay, we can look at a reaction, we can say for sure that reaction will happen. Now, remember, we're not talking about how fast it's going to happen. We're just saying that it will happen. Okay? What about the converse? If the enthalpy change is positive, and the entropy change is negative, both of those factors are counter to what nature would prefer. Right? Both of those do not favor spontaneous reactions. So, what that means is, can that reaction happen? It might happen, but it absolutely requires outside help. Right? It's non-spontaneous. Whether that outside help is electricity, heat, mechanical manipulation, whatever it is. The point is it won't happen spontaneously. Okay. Now we got a couple of mixed bags. So if the enthalpy change is negative, that's favored. But if the entropy change is negative, that is not favored. So now you have two factors that compete against each other. So can this reaction be spontaneous? Well, yes, it can, but only if the enthalpy effect, the one that's favored, outweighs the entropy. And that's gonna occur at low temperatures. The enthalpy effect will be greater than the entropy change, and that happens at low temperatures, and you'll see why in just a second. Okay, last case scenario. Your enthalpy is positive. That is not favored, but your entropy is. So you have two competing factors again. How could this happen? Well, this will happen when the entropy effect is greater than the enthalpy effect, and that occurs at high temperatures. All right, so first of all, when evaluating a reaction, how will you know what the delta H is and what the delta S is? You will calculate. You will use the values from your table and you will solve for delta H. You will get a sign, a value. You will solve for delta S. You will get a value. And if the delta H is negative and the delta S is positive, it is for sure spontaneous. If it's the other way around, it's for sure non-spontaneous. And then if it's a mixed bag, well, it just depends on what the temperature is. So I know that's kind of obtuse, me saying what the temperature is going to be. So there's actually a way to solve mathematically. The be-all, end-all, Gibbs free energy. This is the ultimate determiner of whether the reaction will happen, because we will solve for the Gibbs free energy, which we use the symbol G for. All right, so G. Gibbs free energy is the total available energy that can do work, and it is correlated by the following equation. The change in enthalpy for a reaction minus the product of the Kelvin temperature and the change in entropy. This determines what the delta G value is, the free energy available for work. Right? And a reaction is considered spontaneous only when the delta G value is negative. Must be negative. So, if you went through and you calculated delta H and delta S, you're going to plug those values in, you're going to multiply the delta S by the temperature, and then you're going to subtract from delta H. If the resultant value is negative, then yes, you have a quantifiable spontaneous reaction. Okay? You plug them in, and you have the means. You'll always have of course, you're not expected to memorize any of those values. You'll have them available to you, whether they be in the problem or whether you use in your sheet. Now, your sheet also does have delta G, Gibbs free energy of formation values, and probably the faster way is to calculate the sum of the free energy of the products minus the reactants to find the delta G of the reaction. That's a shortcut that will give you the same value, right? Instead of doing delta H separately and then delta S separately and plugging them in that equation, if you have the delta G values, you can do that. But I'm going to tell you that on the AP exam, they will not give you delta G values. So it's kind of a moot point. So you will need to calculate delta H and delta S independently. Yes?
What units is delta G usually
kilojoules per mole.
Okay.
Yeah, kilojoules per mole. So that's a good point here. Let's evaluate the unit work here for a second. So let me find some space here. Delta G is equal to delta H minus T delta S. So remember that in your enthalpy is kilojoules per mole minus the temperature, which will be something Kelvin, right? And then your units for entropy are joules or kilojoules per mole Kelvin. And so because the entropy has the Kelvin component, in order for the cancellation, you have to multiply the entropy by the temperature in Kelvin. And then at that point, now you're just subtracting kilojoules per mole from kilojoules per mole. And hence your unit will be in kilojoules per mole. All right. So let's pull up your enthalpy chart data. And I want to calculate two things. I want to calculate delta H and delta S, and then we're going to calculate delta G. And this says standard conditions, so that means 298K. So what I do, just a little pointer, little tip, I just literally look the values up and I write them above the reactants and products on the sheet, just so that I know which one is associated with which. All right, so I'm going to open this up here. All right, for the sake of brevity, I'm just going to write them on here. But make sure that you know where I'm getting these from. Okay, so for the iron 3 oxide, it's entropy negative 284. I'm sorry, I said entropy, I meant enthalpy. The enthalpy is negative 8. Oops, got that backwards. Negative 824. The oxygen should not have an enthalpy of formation because oxygen is in its standard state. Remember that, how if it already exists in that state, its enthalpy is 0. And iron, same thing. Iron would be 0. Let's change colors for S. Let's look up S. Okay, so for the iron 3 oxide, the entropy is the second column. And that is 0.0874. And remember, that is in kilojoules per mole Kelvin. I put that in the wrong place. Let's move that. There we go. Okay. For oxygen, the entropy, the molar entropy is 0.205. And then for the iron, okay, so for the iron, it's 0. Nope, just kidding. 0.0273. Looking at the wrong column. Okay, so delta H, products minus reactants. So the product is Fe2O3, so you're going to have negative 824 minus 0 plus 0. Okay, well, delta H for the reaction is negative 824 kilojoules per mole. For the entropy, we've got 0.0874 minus 0.205 plus 0.0273, and we have coefficient on oxygen of 3, and iron is 2, so we can't forget those coefficients. All right. For my change in entropy, I get negative 0.582. Okay, so we just plug them in. Delta G is equal to negative 824 kilojoules per mole. That's my delta H minus the temperature, which they said was standard, 298 Kelvin, multiplied by negative 0.582 kilojoules per mole Kelvin. Kelvins cancel. Let's see what we get. All right. The outcome is that my delta G is negative 650 kilojoules per mole. It is very negative. This reaction is still very much spontaneous. So we just answered the question, will a piece of iron rust? Yes, it will. Just ask my neighbor who's got a VW bug under a tarp behind his shed. Okay. That's a good place to stop right now.